lecture we see the fixed charge transportation problem. We have already seen this formulation of the fixed charge problem in a previous lecture, where I have explained that this problem becomes significant when there is a fixed charge of transporting from a given source to a given destination. We have also seen that the toll that is paid while moving items from I to j could represent the fixed charge between I and j. There could also be other fixed costs that are associated with travelling from a particular place to some other place. So, the fixed charge transportation problem has two components, Cij xij plus Fij yij. The objective function is to minimize the two costs. So, minimize Cij xij plus Fij yij. So, the decision variables xij represents the quantity transported from I to j, and yij represents if arc ij is chosen. So, yij is a binary variable, it is equal to 0 or 1, it is equal to 1 if we choose to transport from I to j, and it is 0 otherwise. Xij is the quantity that is transported from I to j. On the face of it, it appears that this objective function is similar to that of the multi-stage transportation problem, but it is not so. In the multi-stage transportation problem that we saw in the previous lecture, we had an I, j and k. So, there were 3 entities. Now, we have only I and j, we have 2 entities. So, it is very similar to the regular transportation problem, where there are only 2 entities, a set of supply points which may be warehouses, and a set of destination points which could be retailers or customers. So, there is only one stage and there are 2 entities, and the material flows from one set of entities to another set of entities. Typically, material we could think in terms of 3 supply points and 3 demand points, and items flow this way. Now, there is an Ai which is the supply available here, and there is a Bj which is the requirement for this. Now, there is a Fij which is a fixed cost, and a Cij which is the unit cost of transportation if we move from I to j. So, we have typical constraints which will be whatever goes out of this should be less than or equal to Ai. So, sigma xij summed over j is less than or equal to Ai. Whatever that reaches here should be greater than or equal to Bj. So, sigma xij summed over I is greater than or equal to Bj. So, once again the same caution that the balanced problem would have total supply equal to total demand, in which case we can even change this with equations. All the items will be transported and all the items will be received. We will not be receiving more than what is demanded, because the Cijs and the Fijs are not, none of them are negative. Therefore, there will be a solution where all these are consumed and all these are taken. Now, if we have a situation where the total supply exceeds the total demand, then all the demand will be met, more than the demand will not be given, because if we have to transport more than the demand, the total cost will only increase, and some of these supplies will not be utilized fully. So, the same structure will hold. Only if we have a situation where the total demand is more than the total supply, then this formulation would give us infeasibility, because it will not be able to meet all the demand. In such cases, what we do is we balance it by creating another supply, and then say at the end, after solving, that whatever goes out from this supply actually does not go, and therefore correspondingly some of them will get less than what is demanded. So, we need to observe that, particularly when we have a situation where the total demand exceeds total supply, we have to be a little careful in using this formulation, but when we choose to use this, we have to create another dummy supply or a non-existent supply. Now we also have to relate the Yij variables to the Xij variables. So Xij is less than or equal to m into Yij, which means that if I am transporting from a particular I to j, then I have to choose that arc first and then I transport, which means when I choose that arc, I incur the fixed cost of transportation. So I incur the Fij. So only when I choose, I will be able to send. And this big M is a very large number. So when I choose, I can send as much as I can. And if I do not choose this, I cannot send. So when Yij is 0, Xij will automatically be 0. So we will now have, if there are m supply points and n destination points, there are m into n Xij variables and there are m into n Yij variables. So it has 2 times mn variables, where this mn Xij variables are continuous variables, they need not be integers. The other m into n are binary variables, these Yij's are binaries. So we have a problem that has binary variables as well as continuous variables. Now there will be m constraints that relate the supply, there will be n constraints that relate the demand, and then there will be m into n constraints that link the supplies to the demands. So this fixed charge transportation problem, which has an additional fixed charge on the arc, will now have 2 into mn variables, where mn are binary and the other mn are continuous, and it has m plus n plus mn constraints, where these m and n are the supply demand and these are the linking constraints that link the Xij to the Yij. So Yij's are binary and Xij are greater than or equal to 0. Now we can solve this as an optimization problem, like a mixed linear integer programming problem, where some of these variables are binary variables, some of these variables are continuous variables. Now we can solve this to get the optimum solution to this problem. So let me look at a 3 by 3 problem that we have already seen and try and add a fixed charge to it. So we look at this 3 by 3 problem. We look at the same problem that we saw in the previous lecture to explain the transportation, except we also add a fixed charge to it. So the fixed charge is now shown here. So the fixed charge is 100, 120, 110. So 100, 120, 110, 80, 120, 60, 80, 120 and 60, 120, 80 and 60. So 120, 80 and 60. So the values shown here are the Fij values and the values shown here are the Cij values. Now if all the Fij values are 0, which means there is no fixed charge, the problem will become automatically, it will become a transportation problem. So if all of them are 0, then there is no need to have this set of constraints, so it will become a transportation problem. Now for the purpose of illustration, let us look at the optimum solution to the transportation problem without the fixed charge, and then let us see how the solution looks like. We said x12 is 20, x13 is 10. So x12 is 20, x13 is 10, 40, 20, 40, 23 is 40, 31 is 20, and this will be 40. So, this is the optimum solution to the transportation problem without the fixed charge. So, the Cij Xij component of this is 20 into 6 120 plus 80 200, 200 plus 240 is 440, 440 plus 80 is 520, 520 plus 320 is 840 that we saw. Now, if we have to look at this solution and implement the fixed cost associated with the transportation, then we would be incurring a 120 here because we have used this, we will incur 110 here because we have used this, we would incur a 60, we have used this, we would incur another 120 and we would incur another 80. We have already seen that as a transportation problem there will be 5 allocations here because the problem is balanced and non-degenerate. So, this would give us a cost of 490. So, the total cost will be 840 plus 490, which is 1330. Now, this is a feasible solution to the fixed cost transportation problem. So, what we have done is we have not actually solved the fixed charge transportation problem, we have actually solved the transportation problem without the fixed charge, and then we have added the fixed charge to it to try and get a solution whose cost is 1330. But if we solve this formulation of the fixed charge transportation problem, the formulation that we have written here, and for this example as I said there will be 9 plus 9 18 variables, there will be 3 plus 3 6 constraints plus another 18 constraints. So, 24 constraints and 18 variables. If we solve this problem optimally, our solution would be x11 is 20. So, let me write it with a different color. So, x11 will be 20, x13 is 10, x23 is 40. So, x13 is 10, x23 is 40, 32 is 60, x32 is 60. This is the solution. So, 20, 10, 40 and 60 is the solution, optimum solution to the fixed charge transportation problem. So, let us try and evaluate the costs associated with it. The cost of transportation is 20 into 480, the fixed cost is 100. The cost of transportation is 10 into 880, the fixed cost is 110. The cost of transportation is 40 into 6 240, fixed cost is 60. Cost of transportation is 60 into 8 480 and this cost is 80. So, now this will be 8 plus 4 12 20 28 to 880 and this will be 350. So, the total cost will be 1330. So, the cost will be 1230. Now, the solution that is shown here, this is the optimum solution to the fixed charge transportation problem by solving this formulation. Now, we compare this solution to the other solution where we evaluated the total cost by considering the fixed cost. Now, 1330 was the cost here, while the cost is 1230 here, there is a saving of 100. We also realize that there are only 4 variables in the solution here. This cost has come down this cost has marginally gone up, but this cost has come down. The very fact that there are only 4 variables in the solution implies that we are going to have 4 arcs in the solution and only 4 fixed costs, whereas this would force us to have 5, and then there were 5 fixed costs, and then we realized a lot of saving there, which has resulted roughly in the saving of 100. Though this has gone up a little bit, this has gone down significantly to give us a saving of 100. So, a fixed charge transportation problem, if we have the fixed charge assumption and there is a cost associated with it, then we need to look at this formulation and then solve it. So, the next question that comes is, can we have another method like our minimum cost method or the stepping stone method to try and actually solve the fixed charge transportation problem without the formulation? A very simple thumb rule would be now to define C dash ij is equal to Cij plus Fij by Mij. So, let me explain this thumb rule. Now, let us look at the same 3 by 3 problem. Now, the unit cost of transportation from 1 to 1 is given by 4 and the fixed charge is 100. Now, the supply that is available here is 30 and the demand is 20. So, if we consider this position, so C dash ij will be Cij, which is 4, plus Fij is 100 divided by Mij is the minimum of this and this, minimum of the supply and the demand. So, minimum of 30 and 20, which is 20. So, this would give us a number equal to 9. So, I am going to write this number here, this number is 9. So, like this we can calculate this number which captures both Cij as well as Fij into to get a new number which is called C dash ij, which could represent some kind of an equivalent cost considering both the Cijs and the Fijs. The motivation comes from the fact that this fixed charge, if we are going to use this to transport, we are incurring an additional charge of 100. Now, this additional charge of 100 is used in transporting from this to this. The maximum that can be transported from this to this is the minimum of the two numbers 30 and 20, which is 20. Therefore, this 100 should be used in transporting a maximum of 20 from this to this, which is the minimum of this 30 and this 20. So, per unit the apportionment of the fixed cost can be 100 by the minimum of these two, which is 100 by 20, which is 5, and therefore, C dash ij becomes Cij plus Fij by Mij. So, this way we can complete the calculations for C dash ij, and then the values now become 9, so the values become 9, $10, 11.66, $10, 10 and 7.5, $10, 9.33 and 13.2. So, let me again explain this 13.2. The 13.2 would come as 12 plus 60 divided by the minimum of these two. So 12 plus 60 by 50, 12 plus 1.2, which is 13.2. Now we can solve a transportation problem with 30, 40 and 60 and 20, 60 and 50. So this becomes the normal transportation problem, and when we solve that transportation problem we would get a solution which is 20, 10, 40 and 60. So we will get a solution like this, and the cost associated with this will be different. It will not be 1230, it will be different. But once we get this optimum solution, we now have to go back and map this optimum solution here and then try to find out the fixed cost as well as the transportation cost. Transportation cost will become 880, fixed cost will become 350, and the total will be 1230. If we do 9 into 20 plus 10 into 11.66 and so on, that will be different. So it will not be 1230. We have to do that separately and try and get the cost to the original problem. But this thumb rule need not give us the optimum solution all the time. In this example it has given us the optimum solution. There could be instances where this thumb rule may give a cost that is actually higher than the cost given by the optimum solution, which is solved using the integer programming. That is because from an operation research point of view, the fixed charge transportation problem is a hard problem, and therefore we do not have effective thumb rule based methods which can give the optimum solution in all the instances. In some instances it may give the optimum solution as it did in our example. So if we really want the optimum solution to the fixed charge transportation problem, then we can solve this or use this and use a solver to solve this, which again necessitates the availability of a solver. And if we do not have a solver, we could think in terms of other methods such as a branch and bound algorithm and so on. Such methods exist in the literature, they can be used to get the optimum solutions. At the same time, if we are not very keen on the exact optimum solution, but if we are content with a good solution which can be slightly higher than the optimum in some instances, but a good performance on an average, one could look at this thumb rule and then create an equivalent transportation problem from the fixed charge transportation problem, then solve it and get the solution. So we can do that as well. The next problem that we will look at is what is called a point to point, one warehouse, one retailer problem. Simple point to point, one warehouse, one retailer problem. Now let us assume we explain it through a numerical example. So we will assume now that we want to transport 41 tons of items from this warehouse to this retailer. Now in order to transport these 41 tons, we can do that using different types of trucks. So let us assume we are looking at two types of trucks. One truck can carry 16 tons per truck and the other can carry 9 tons per truck. Now the cost of hiring and using this is 10 and the cost of hiring and using this per truck is 7. So the question boils down to how many of these trucks do we take, how many of these trucks do we take such that we are able to transport the 41 tons and we are able to do it with minimum cost. So the problem would be let x1 be the number of 16-ton trucks used, let x2 be the number of 9-ton truck used. So, the total cost will now be 10x1 plus 9x2 or 10x1 plus 7x2 plus 7x2 is the total cost, which has to be minimized, subject to, if I am using x1 trucks of this type, I can carry 16 x1 items. If I use x2 type trucks of this type, I can carry 9x2 is greater than or equal to 41. So, the problem is to find out x1 and x2, that minimizes 10x1 plus 7x2 subject to 16x1 plus 9x2 greater than or equal to 41, x1 x2 greater than or equal to 0 and integer. Now, the integer is extremely important because we can only hire an integer number of trucks. So, it becomes a very simple linear integer programming problem, and if we are going to consider only point to point from one supply to one destination or one warehouse to one retailer, there is going to be only one constraint. So, this is a single constraint integer programming problem, all integer problem, because both x1 and x2 will have to be integers. So, there is an objective function that is to be minimized, there is a single constraint and there is a all integer. Now, this problem is called a single constraint knapsack problem. The standard single constraint knapsack problem is a maximization problem with a less than or equal to constraint and variables greater than or equal to 0. Now, this version of the knapsack problem is a minimization problem with a greater than or equal to constraint. Nevertheless, it is also a knapsack problem. So, one need not look at it as a different problem. The original knapsack problem talks about putting items into a knapsack such that the value that we put in is maximized. Xj is the number of units of different items that can be put in. Now, this coefficient could represent, there is a single constraint which could either be a volume constraint or a weight constraint, not both. If we have both, then it becomes a two constraint problem. So, it is a single constraint, and if it is a volume constraint, this would represent the volume of each item, and the volume that we put in should be less than or equal to the volume available. So, it is a maximization problem with a single constraint of a less than or equal to type. This version of the knapsack is a minimization problem with a single constraint which is greater than or equal to type. The same problem can become a little different if we have different warehouses and different retailers, or if we have one warehouse and multiple retailers, R1, R2, R3 and so on. This person may require 41, this person may require 52, this person may require 37 and so on. So, again we may have to now define x11 and x12 as the number of trucks of 16 ton and 9 ton, x21 and x22, x31 and x32 and so on. As long as there is no availability restriction on the number of 16 ton trucks and the 9 ton trucks, the problem can be separated into several single constrained knapsack problem, one for each arc. But if there is a capacity restriction or the availability restriction on the number of 16 ton trucks and 9 ton trucks available, then we would get, then it would simply become 10x11 plus 7x12, there will be another 2, 1, 2, 2 and all that, and then there will be a constraint which will say x11 plus x12 plus x13 plus x1n will be less than or equal to the available number of 16 ton trucks. So, we could have another set of availability constraints and the problem becomes very different. It is not a single constraint knapsack problem anymore. Right now, let us restrict our discussion only with a single retailer or a single customer, and therefore we will have the single constraint knapsack problem. If again we have a solver, one can easily solve this using the solver, there is only a single constraint. If we have only two variables and a single constraint, one can even do an enumeration and try and solve it, but then there are better ways of actually solving this using some kind of a branch and bound algorithm. Now if we use only 16-ton trucks, then we will require x1 equal to 3, which is upper integer of 41 by 16. So we will need 3 trucks here and the cost will become 30. If we use only 9-ton trucks, then we would need 5 such trucks. So I would have 5 and then the cost will become 7 into 5, which is 35. So we could simply think in terms of an enumerative algorithm. So we can simply enumerate and say x1, x2. So x1 is 0, x2 is 5, cost is 35. x1 is 1, so then we have 1 here. So this would give us a capacity of 16. So from here we need a capacity of 25. So we will have 3 here. So 1 into 10 is 10 plus 21 is 31. If I have 2 of this, so I have 32 out of this, I require only 9. So 2 comma 1, so I will have 27, and I will 3 comma 0, I will have 30. So only 4 enumerations are possible in this case, and the best solution is here, which is use 2 16-ton trucks and 1 9-ton truck to get this 41 and with a total cost of 27. But then we can also understand that the enumerative method that we have shown here is not computationally efficient and can become intractable when some of these numbers become higher. Therefore, the single constraint knapsack problem also becomes a hard problem, and some efficient methods such as branch and bound algorithms are also available, which essentially do the complete enumeration, but they do what is called implicit enumeration. They do not do a complete enumeration explicitly. Now by creating some bounds, it is possible to reduce the number of computations here to a meaningful number and then to try and get the best solution using branch and bound algorithms or implicit enumeration algorithms, which reduce the number of explicit enumerations and tries to give us the optimum solution. I have actually outlined the branch and bound algorithm to solve a single constraint knapsack problem with a maximization objective and less than equal to constraint in the advanced operations research course, where we look at the cutting stock problem. A very quick note on this, we can also do this. So what we can do is, this is a minimization problem. So this is a minimization problem. If we can solve it as a linear programming problem, an LP solution to it, which means we are ignoring the integer restriction. Since it is a minimization problem, we can actually sort the variables in terms of the ratio 10 by 16 and 7 by 9. 10 by 16 is like 0.6 to 5, 7 by 9 is 70, so 9 sevens are 63, 70.77. So LP solution would give us x1 equal to 41 by 16, which is 2.90, so 16 5s are 80, 100, 6 are 96, 40, 2.5625, and cost equal to 25.625. So this will be the LP optimum. It would choose, because there is only one constraint, the LP will choose only one variable, and it will choose that variable which has the smaller coefficient. So it will choose x1 and give it a value 41 by 16. So 25.625 will act as a lower bound to this. So we can start the problem by saying x1 is equal to 2.5625 with lower bound equal to 25.625, which makes it 26. Now from this, since x1 equal to 2.5625, we can branch off with x1 equal to 0, x1 equal to 1 and x1 equal to 2. And then when x1 equal to 0, we will solve another LP. So when x1 is equal to 0, this would, we are solving an LP that minimizes 7x2 subject to 9x2 equal to 41. So x2 will be 41 by 9 and objective function value z will be 41 by 9 into 7. So 41 into 7 by 9, 287 by 9, which is 9 3s are 27, 180, 9 8s are 72, 31.88. Now we look at this one. Now the feasible solution for this will be x1 equal to 0, x2 equal to 5 with z equal to 35. Now this gives us an upper bound for this. Now when x1 equal to 1, we will now have a solution, x1 equal to 1, x2 equal to 25 by 9, 25 by 9 is 9 2s are 18, 70, 9 7s are 63, 2.77. Now z value will be 10 plus 25 into 7 by 9, 175 by 9. This is 10 plus 9 1s are 9, 85, 9 9s are 81, 40, 9 4s are 36, 19.44, 29.44 is the lower bound, and the corresponding feasible solution is x1 equal to 1, x2 equal to 3 with z equal to 21 plus 10, 31. Now x1 equal to 2 would give us x1 equal to 2, x2 equal to 1 with z equal to 27. So this is integer feasible, and this integer feasible is lower than both the lower bounds, and therefore it is optimum. Now the branch and bound algorithm that we have seen borrows ideas from lower bounds and upper bounds to between LPs and IPs. So it involves certain operations research ideas, and right now I am just explaining it to show that it is actually optimum. A little more detail and depth and a detailed way of representation of this, as I already mentioned, is considering a maximization problem with a less than or equal to, which I have explained in further detail in the advanced operations research course, where we address the cutting stock problem. Now this branch and bound method is another method which is slightly different, similar and different to the enumeration method that we saw here, and gives the optimum solution of 27. But as I mentioned, if we expand this problem to multiple retailers, and more importantly keep a capacity restriction on the number of trucks available of different types, in practice it need not be only 2 types, it can be multiple types. The problem becomes much more complex for us to come, and much more complex, the problem does get much more complex, and it has to be solved using integer programming. The next model that we can see is one warehouse and multiple retailer, which is a logical expansion of this. But the problem is slightly different here. There is a single warehouse, there are multiple retailers, and so on. Now we will assume that there is a truck which goes from here point to point, it goes to the retailer and comes back, and then it can go from here to another retailer and come back, and a third retailer and come back, and so on. So, let us assume that the retailer j, there is a distance of dj which the truck covers, let us say both ways put together there is a distance dj, which is this into this plus this into this is dj. Now, we will assume that there is a single truck which is going to transport. So, whatever quantity that is transported from here to here is less than or equal to a single truck load, and or but we also do point to point, which means from here it goes, it will come back, and then it will go to here or some other place and come back. Now, we have, if there are j equal to 1 to n retailers, so we will have dj values d1 to dn. Now, the total time required by the truck, by a single, if a single truck has to do it, the total time required is the sum of d1 to dn. But if this truck is available only, now we will call this time as, using this notation, we would call this time as t1 to tn. Instead of distance, we call them as time tj, j equal to 1 to n, and the truck is available only for a time of capital T. Then the question is, how many trips should this truck take, or how many trucks do I need such that I meet the demand of all of these T to n. So, now that problem is called a bin packing problem. It is called a one dimensional bin packing problem, or it is called a bin packing problem, and the problem is very similar to saying that I have bins of height t, and then I need to put items into this bin. I have n items, each item has a height, the jth item has a height tj. So, I have to put these items one above the other, it is a one dimensional bin. So, I need to put them one above the other such that I do not exhaust the height of the bin. How many bins do I need so that I can pack all these n items where the jth item has tj is a one dimensional bin packing problem. Problem can also be explained in different ways. I have several sticks of length capital T. Now, I need to make smaller sticks, n number of sticks with each length equal to tj. How do I break these longer sticks to get these lengths, and I have to use the smallest number of such long sticks with length t. What is the minimum number of the longer stick with length t that I require, through which I can break them and get these tj n lengths where the j smaller stick has a length tj. That is another way of looking at this. The third way to look at this is, given n numbers t1 to tn, form minimum number of groups such that the sum of the numbers in each group is less than or equal to capital T. All these is a description of what is called a one dimensional bin packing problem. So, the formulation of the one dimensional bin packing problem will be like this. Now, we are going to assume that there are n items with values t1 to tn, and there is a bin with length t where we need to put in. Now, we want to minimize the number of bins. So, we will assume now that y1 to yn represents the number of bins that we have. It is fairly obvious that if each of these is smaller than t, which is not a bad assumption, then we can take, since there are n items, we can take n bins and put each item into a bin. So, that would give us a solution with n bins, but that is not what we want. We want to have the number of bins to be as small as possible. So, what we do is, we would assume right now that we have n bins, and then try to minimize the number of bins. So, we would say minimize sigma yi I equal to 1 to n, yi equal to 1 if bin I is chosen. So, by minimizing the number of sigma yi, I essentially try and minimize the number of bins that I choose. So, the objective function would be this. Now, what are the constraints? Each item should go to only one bin, and before that I need to introduce another variable xij equal to 1 if item I goes to bin j. Item I goes to bin j. So, I will now say sigma xij equal to 1 summed over the bins j, or let me look at it slightly differently. I have used subscript I for the bin, so I would use subscript j for the item. So, item j goes to bin I. So, summed over all the bins xij equal to 1 for every item j. So, every item j will go to exactly one bin, which is given by this constraint. Now, as far as the bin is concerned, sigma xij summed over j, they are the items that go to a particular bin, and tj now is the length of the jth item. So, tj xij is the length associated with this bin. Now, this should be less than or equal to t that we have, which is the overall bin length, and then this should be less than or equal to t into yi for every I. So, yi is equal to 1 when the ith bin is chosen, and when the bin is chosen it gives us a capacity of t, and then whatever that goes into the bin should be less than or equal to this. So, this is one way of doing it. The other way of doing it is what is shown in this slide, and these are explicitly written as two different constraints. So, we could simply say tj xj less than or equal to t, which means that we need to have a linking constraint between the xij's and the yi's. Now, we could also write xij is less than or equal to m into yi, which means only when the bin is chosen I can put something into the bin. Now, this has more constraints. So, this constraint can be eliminated by simply putting t into yi. Now, this is the formulation of the bin packing problem. So, both yi and xij's are binaries. Now, one can solve this bin packing problem to try and get the optimum solution, but the way we have formulated, for example, if we have 10 items, then we are talking of, we are now also defining yi. So, y will take 10 values and xij will take 100 values. So, we will have 110 variables, and this formulation will be, for this will give us 10 constraints, this would give us 10 constraints. So, there will be 20 constraints. So, if we actually solve a problem with 10 items using this formulation, we would have 110 variables and 20 constraints. We can do that. Alternately, we could think in terms of some other heuristic or thumb rule based algorithms, which would say that we may be able to pack this, instead of a maximum of 10, we will be able to pack it in say 4 or 5 bins. Then if we restrict the number of bins from 1 to 10, we can bring it down to 1 to 5, then the number of variables and constraints will reduce. So, it is customary to look at a heuristic solution to the problem, then find out a certain number of bins, and then solve the optimization by taking advantage of the fact that a heuristic solution would actually result in lesser number of variables and constraints. So, we will look at some of the heuristic solutions to the bin packing problem in the next lecture.